Ever wonder how a chatbot actually knows if it gave you a good answer? Or how your favorite streaming service figures out what you really want to watch next? Well, the truth is, a lot of the time, they're just guessing, based on our really messy, mixed signals. So let's get into it and explore the super clever way AI is learning to listen. A whole lot better.
See, at the heart of all this is a huge challenge for any learning system, what we call the AI feedback problem. And it really just boils down to a simple fact. Not all feedback is created equal. The AI is basically getting two totally different kinds of clues from us. And this slide breaks it down perfectly. On one side, you have noisy feedback. This is the stuff that happens all the time. Think about it. You hit stop generating on a chatbot. So why'd you do that? Was the answer terrible, or did you just get exactly what you needed and moved on? The AI has no idea. So it's frequent, but it's a really unreliable signal. On the other side, you've got sparse feedback. Now this is the good stuff, the gold. This is when you go out of your way to give a thumbs up or a 5-star rating. It's incredibly valuable, but let's be real, we almost never do it. It's super rare.
So that brings us to the million-dollar question, the one that researchers from IBM, Orange Lab, and Columbia University set out to answer. How on earth can an AI learn and get better when it's drowning in all this noisy, confusing data and only gets a clear, valuable signal once in a blue moon?
To figure this out, the researchers did something really smart. They didn't start from square one. Instead, they turned to a classic analogy from a field called decision theory, a row of good old-fashioned slot machines.
This is what's known as the multi-armed bandit problem. Just picture it. You're in a casino, standing in front of a whole line of slot machines, or arms. You've only got a handful of tokens, and your goal is to walk out with the most money. The catch? You have no idea which machine pays out the most. The only way to figure it out is to start playing.
And this leads to the core dilemma, what's called the exploration versus exploitation trade-off. Do you keep pulling a lever on the machine that's been paying out okay so far? That's exploitation. Or do you risk a few of your tokens to explore a new machine that might be the real jackpot winner? That's exploration. This exact trade-off is at the very heart of how AIs learn to make choices.
Okay, so let's bring it back. How does this whole slot machine idea help us with our problem of noisy clicks and rare likes? So here's the clever twist. Imagine that every time you pull a lever, you get two kinds of rewards. You get a constant little stream of pennies. That's our frequent noisy feedback. But also, every once in a great while, you might get a jackpot ticket. That's our rare, super valuable, sparse feedback. So the entire game is to find the machine that gives out the most jackpot tickets. But almost all the information you have to go on is just the pennies.
So how do you find that jackpot machine without getting totally fooled by the constant stream of pennies? Well, this is where the researchers developed an algorithm with a really clever trick up its sleeve.
The big idea, the aha moment, isn't to just throw away all that noisy feedback. I mean, it's still data. No, the secret is to use the rare jackpot tickets to verify if the penny payouts are telling you the truth.
Now this slide looks a little technical, but the idea behind it is actually pretty simple. On the left, you see the problem. That wide, messy green curve represents the noisy penny feedback. It's unpredictable. The tall, skinny blue spike is our rare jackpot feedback. It's super precise. The new algorithm, called IUCB, uses that precise blue signal to build statistical guardrails. That's the walled-off area you see on the right. Then it looks at all that noisy green feedback and says, anything that falls outside these walls is probably just a fluke. So it's not ignoring the pennies, it's just filtering out the ones that seem way too good or way too bad to be true.
Okay, so this filtering idea sounds smart, but does it actually work? Well, the researchers set up a race to find out. They pitted their new algorithm against two other strategies to see which one could learn the best choice the fastest with the fewest mistakes.
So, let's meet our contestants. First, there's SUCB. We'll call it the patient one. It completely ignores all the noisy pennies and only waits for those rare jackpot tickets. Then we have SNUCB, the gullible one. It trusts everything, just lumping all the noisy and sparse feedback together without a second thought. And finally, our new contender, IUCB, the smart one, which uses all the feedback, but with that intelligent filter.
Before we see the results, let's talk about how we're keeping score. The metric is called pseudo-regret, which is just a fancy way of saying total mistakes or missed opportunities. Every time an algorithm picks a less than optimal slot machine, its regret score goes up. So, on the graphs we're about to see, just remember, a lower line is a better score.
And here we go, the results from the first race, with 30 different options. It's not even close. The blue line, our patient algorithm, makes a ton of mistakes. The green line, the gullible one, does a bit better. But look at that red line, our smart filter, IUCB. It is consistently the lowest by a long shot. It's learning faster and making way fewer mistakes.
So, what happens when we make the problem a lot harder? Let's jump to a race with 100 different options. Whoa, the gap gets even bigger. The patient one, SUCB, gets even worse. The gullible one, SNUCB, struggles. But our smart filter, IUCB, the red line, is still cruising with a commanding lead. This proves the filtering strategy wasn't just a fluke. It's a really solid approach that works even when things get way more complex.
So the verdict is in. The smart filtering approach is the clear winner. It proves that the best way to handle messy feedback isn't to ignore it, but to intelligently verify it.
Okay, this is all fascinating stuff, but why should you care? What does a winning slot machine algorithm really mean for you in your day-to-day life?
Well, it means smarter, more efficient AI pretty much everywhere. This kind of thinking leads directly to better movie and product recommendations that can actually understand your subtle cues. It means more helpful chatbots that don't get confused so easily. It means AI systems that can learn new things a whole lot faster. And yes, it even helps create more effective and maybe less annoying online ads.
And what's really key here is just how foundational this research is. The authors say it themselves. This is the very first time anyone has formally studied how an AI can learn from two different kinds of feedback at the same time. This is basically paving a whole new road for making AI that's more tuned in to how we humans actually communicate.
So that kind of leaves us with a final thought. We are constantly teaching the AIs all around us. So the next time you give a thumbs up or just close a window, remember that you're giving it a clue. You're either handing it a rare, valuable jackpot ticket, or you're just giving it another noisy penny. The question is, what kind of teacher are you going to be?